Welcome, ladies and gentlemen, to your study of geometry. We are here at the very beginning, at the basics of geometry, to start laying a foundation, to start coming up with some words, some phrases, some ideas that we will use throughout our study of geometry in order to know what we're talking about and be able to communicate with each other. So I'm going to go through some stuff that's pretty much the foundations of geometry, the building blocks of geometry, and I'm going to go through it pretty quickly because a lot of it might be familiar to you, but it's all very important. And there are even some small details that are really important. So I want you to stay with me. And one of the things I want to point out to you is that I'm going to go fast because it's a lot, and that you got to remember that you are watching a math instructional video. And when you're watching a math instructional video, you don't watch that like a TV show. You watch that ready to hit pause at any time and maybe go back a little bit and listen to something again if it didn't make sense to you. Maybe write something down. Maybe just hit pause and think about it for a second. Make sure it makes sense to you. But make sure that you are watching this in an engaged fashion so that you can get out of it what you need to get out of it. So, geometry is not something that people came up with or discovered. Well, my phrasing is all over the place. Sorry. A lot of times people are like, who made up this stuff? Who made up math? It's not as much that we made it up as that we figured it out. Okay? Math is part of the principles of how the universe works. And when it comes to who came up with geometry, basically we got this guy back in 200, 300 BC, or BCE, named Euclid, one of the ancient Greeks. So here is Euclid. I'm pretty sure that's not the best likeness of him, but there he is. And Euclid is considered the father of geometry because it's not that he made geometry up. It's that there was all this mathematical knowledge, but it wasn't organized. And he said, I've got to get this together and organize it and come up with a system where we can study this stuff and make sense of it and make sure that what we're saying makes sense and that we can build on things that have a good foundation. And so that is why what you are studying is actually called Euclidean geometry. He wrote this book, or this series of books really, called The Elements, that was basically just an organizational system for the math that was known to that point, largely geometry. And this book was used. Think about how long books stay on the bestsellers list. This book was used as the main textbook for geometry from about 300 BCE all the way to the late 19th century. So we're talking 2,000 years. It was the main textbook, the main thing people studied with geometry. So it was really important, very, very foundational. So let's look at one of his main ideas is that he came up with 3 undefined terms. Now, the idea behind undefined terms is this. You have probably never looked up the word "the" in a dictionary because you already understood the word "the." You understood what it meant. You understood what it was about before you ever saw a dictionary. If you look up a definition of something and you look at that definition, it has words in it. You have to already understand some words to be able to understand a definition. And that's the theory here, is that before we can talk about all these geometric concepts that we need to talk about, we're going to have some foundational things that we say, okay, we just agree that we understand what these mean. And those things are point, line, and plane. So when we talk about these things, it's not that we define them so much as we have sort of like a commonly accepted description or a commonly accepted understanding of what they mean. And the first one, point, is just a location. Okay, now when we think of a point, we like to think about a dot. We say, oh, I drew a point. That is my point. Well, yes, this is how I represent a point. But also no, because what I just drew here has some thickness, it has some width, it has some height. Okay, I can see it. Technically, a point is a location that has no thickness, it has no height, no width, no depth. It's like if you thought about taking a pencil, and I was going to grab a pencil, but I don't see one. Taking a pencil, pretend this is one, and sharpening it as sharp as you could and then making a dot and then going, oh no, that's not sharp enough. Let me sharpen it 10 times as much and make a dot to where you can't even see it. So it's just a specific location, but we can't see a point, so we have to look at something we can represent. So we draw a little dot and we name it by a capital letter. Points are always named by capital letters. So this is a representation of a point, really, more than it is an actual point. Now, when you were in 3rd grade, when you wanted to go to the cafeteria for lunch, you lined up. Okay, so you already know what a line is. Basically, think about all the kids in that line. They're like points. Okay, so we have points and they're in a row. That's really what a line is. But there are infinitely many points on a line. In between any 2 points, there are 2 other points because remember, they don't have any thickness. So I could always fit another one in between 2 other ones. It's almost like all the kids in your line are flat Stanley. So it's like if you keep going forever with points that are in a row, that is a line. So a line is just an infinite series of points. I don't like that line because I didn't draw it exactly on top of where those points were. Still didn't. But there we go. And we represent it like this with arrowheads on both ends because it keeps going forever. Okay? Now, we just said on that line there are infinitely many points. Millions and millions and millions of points. But the special thing about a line is you only have to have 2 points to know where it is. If I pick any 2 points, it doesn't matter where they are, there is one way and only one way to draw a line that goes through those 2 points. You can't draw a different line from mine that also goes through those 2 points. And so we say that 2 points determine a line. All right, so that's how we name a line. If I'm going to name a line, I need to name any 2 points that are on it, and that will tell you which line I'm talking about. They don't have to be, you could have a whole bunch of points written here. Let's say I have a point here and here and here and here. I could call this line QV if I want to, or line QT if I want to, or line VW. I still only use 2 letters, even if I see 1,000 points. All right, now, this is not a complete name of a line. I still have to put something on here. And what I put on here is a little line that goes on the top and has arrowheads on both sides. It has to have arrowheads if I'm trying to describe a line. If I forget to put the arrowheads on, then I'm not describing a line. I'm describing a segment or a line segment. Now, I went a little far there. But if I do this, that is not line QV. Here's line QV. This is segment QV or line segment QV. A line segment is a piece of a line. It's basically those 2 endpoints, Q and V, and all the points that lie between them on that line. So this pink portion that I just highlighted is segment QV. So a segment is a finite piece of a line. Finite meaning it ends on both sides. Finite is the opposite of infinite. Okay, so finite means it ends. So we have just a little piece of a line. And when you are naming either a line or a line segment, it doesn't matter what order you put the letters in. I could call this QV or I could call it VQ, and I mean the exact same thing. Now there's another piece of a line for which that's not true. Let's say I have a line and I say, I'm going to put these points on it, and I want to talk about a ray. Okay, a ray is a piece of a line still, but it has a point that is like an end, and then it goes forever in one direction on the line, basically. All right, so what I have just highlighted here is ray VR. The point that is not on the continuous side, the point that is on the side where it stops, is called the initial point. So it has an initial point, and then it keeps going in one direction on the line. Now, rays names you have to be a little bit more careful with. Ray VR is not the same as ray RV. You cannot just turn it around. If I want to look at ray RV is right here and goes forever in that direction. Completely different ray. All right, so the way we name it tells us the first letter is always the initial point. We always write that first. We always write it on the left. And the next letter, the one on the right, is always the one that tells us which direction to go in from the initial point. Because we always start with the initial point and then this tells me which direction to go from there, the arrow on top always points to the left. I mean, excuse me, to the right. I was about to say, it never points to the left. We don't ever see that. That would not be appropriate. Okay? So you cannot draw the name of a ray, try to name a ray with an arrow that points to the left, because that's not how it works. You always put the initial point first and then tell me which direction, which point it's going toward. So in other words, the arrow points to the right, whether I'm talking about a ray that points to the right or a ray that points to the left or a ray that points up, down, left, right, whatever. This does not tell me anything about which way the ray goes. It's just how I name a ray. Okay, now speaking of points on lines, there is a phrase that tells me about points being on the same line together. Not a phrase, excuse me, a term. And that is collinear. Collinear points are exactly what that word says. Co means together, and see the word line is right in there. Together on the same line, collinear. So points B, D, and H are collinear points. Points A, B, and H are collinear points. A, B, and C are not collinear points. That's called non-collinear. Okay, now, because any 2 points makes a unique line, in other words, if I talk about points A and C, I could draw a line that goes just through points A and C. I don't ever say 2 points are non-collinear. I have to have at least 3 points to talk about non-collinear, because any 2 points do create a unique line. So there's a line that goes through both of them. So you have to have at least 3. So I could say, for instance, points F, D, and H are non-collinear, or points E, F, and D are non-collinear. I can say that B, D, and H are collinear. All right, so collinear is on the same line, non-collinear is not on the same line. Another thing we talk about when we talk about lines and points is that we talk about what happens when you have more than one line. When you have more than one line, there are 3 things that could happen. One is they could never ever touch, and they could be basically in the same flat surface. Okay, we call that parallel. We'll come back to this flat surface idea. The other is they could touch, and if they do touch, they're only going to touch in one point, and that one point is called the intersection. Okay, so those are 2 of the things that can happen when you have 2 lines. All right, if they touch, that point where they touch is called the intersection. Speaking of which, let's talk about what happens if I have a segment and another segment. That wasn't really a speaking of which. Let's pretend that I drew this perfectly and that they are the same exact length. Okay, 2 segments that have the same length are called congruent. There's 2 different ways we could talk about that. Really, congruent means they have the same measurement. So we have talked about naming lines. Let me just get a new piece of paper here. We have talked about how this means a line that goes through A and B. This means a segment that ends at A and B on both sides. I can also do this, though. And this is one of the reasons it's very important that you do not forget to put what you need to put on top, because this has a meaning all of its own. This means the length of segment AB. If you have nothing on top, it means the length of segment AB. Or another way of thinking about that is the distance between A and B. Okay, so I could say that the distance between A and B, or the length of AB, which is a number, the length of something, it might be 17 inches or 3 feet, it's a number. I can say that's equal to the length of QR. And another way of saying that the lengths of 2 segments are congruent is to say, the lengths of 2 segments are the same, is to say the 2 segments are congruent. Now I want you to notice that I did something different when I talked about congruent, which is what this symbol means, versus equal. Okay? Lengths, or any kind of, I wrote the word equal because I said the word equal. Sorry about that. Lengths, height, width, angle measure, any kind of measurement is a number. Numbers are equal. All right? Numbers are equal. Things or objects are congruent. Think about it this way. If Eddie and Fred are the same height, then I can say that Eddie and Fred are the same height. I would not say that Eddie and Fred are the same. I wouldn't just say they are equal, because that implies they're literally the same person. Okay, so that's what we're doing here. I'm going to say segments. This is an object. A segment is congruent to another segment. Its length can be equal to the length of another segment. So when we're talking about numbers, measurements, we say equals. When we're talking about objects, we say congruent, to really say the same thing. All right, next, let's look at a segment. Why not segment? I was going to say AB because it was there, but let's give it some different letters. Segment MN. Segment MN has a set length. Let's say it's, I don't know, 16 inches long. This one clearly is not. If I go 8 inches from either side, then I would be right in the middle. And that middle is called the midpoint. You have probably done at some point in your life a midpoint formula. You may remember that from Algebra 1. We're not doing that right here. Right here, all we're going to talk about is what it means when you have a midpoint. What it does is it divides your segment into two congruent smaller segments. So I'm going to mark little matching hash marks to indicate that this length is the same as this length. And that tells me that's the midpoint. So even if I didn't have that word written there, even if I had just that, I can say, oh, look, that's the midpoint because of those markings. You don't ever want to try to assume you have the midpoint just because it looks like it's in the middle. The markings can tell me that it's a midpoint. I don't assume it just because it looks sort of in the middle. Or the word can tell me that it's the midpoint. One thing that a midpoint does, and it's not just a midpoint that does it, anything that goes right through the middle, it can be a line that cuts through the middle of your segment, is it bisects the segment. To bisect something means to cut it into two equal parts. Now, it's different from the word intersect. Remember, we just talked about intersect. Intersect basically just means they touch each other. They have at least one point in common. Okay? Lines, it's only one point. But other things could intersect. Like I could have two circles intersect, and they would have 2 points in common, maybe, or could just have one. Different ways it could work. But intersect just means they touch. That's all it means. Bisect is much more specific. It means cuts into two equal parts. Okay, and we're talking about equal length. Another way of putting that is two congruent parts, because remember, congruence means has the same measurement or has equal length in the case of a segment. Okay, so this line is bisecting segment MN. A line, a ray, another segment. Lots of things could bisect a segment. But if you do have a bisector, let's go ahead and label this a bisector. If you do have a bisector, then it has to go through the middle point, or the midpoint. A bisector of a segment always passes through the midpoint. Okay, so we're coming in for a landing on this stuff. We circled back to Euclid and his three undefined terms, because we have talked about two of them. That's a check mark. It kind of looks like a V. And we've got one more to talk about, and that's a plane. A plane is basically like a flat surface that extends in all directions except thickness. Okay, so think about the floor of the second story of a building. In other words, you're on the second floor or the third or any floor above the ground floor. Think about the floor, and it separates you up here from the people who are on the floor below you. Pretend that floor just starts growing out in every direction, so that there's no way for you to get around the floor to go downstairs. The only way for you to go downstairs is to punch a hole in this floor and go through it. That's a plane. A piece of paper is a plane. Here's a plane, a flat surface. This is actually a stack of paper, but here I've got a plane. A plane doesn't have to be horizontal like this one is represented. A plane could be vertical. A plane could be neither of those. Let's see how well I can do on this. I did not draw the one I normally draw first, so let's see. Yeah, that's not the best. But yeah, I'm throwing that out, sorry. Let's draw my plane. Still messed it up, but we'll pretend I didn't. Yeah, okay. I messed up exactly the same way I did before. Basically pretend this is dotted. We can't see this part. When you have two planes intersecting one another, they intersect in a line. Basically think of it as where the wall, and that black part is the wall, meets the floor. Where the wall meets the floor, you have a line. A lot of times it's the baseboard. Okay, so here I have a flat surface that is horizontal, that's a plane, and then I have one that's vertical cutting through it. So those are two planes intersecting, and two planes, when they intersect, always intersect in a line. Remember, when two lines intersected, they intersected in a point. Two planes that intersect in a line. Now let's talk about other things going on with the planes. Very often we represent a plane with sort of a parallelogram looking thing, and we can draw things inside that parallelogram to indicate that they are inside my plane. Maybe this line is inside the plane. Okay, let's call it line AC. All right, if I have another line that is inside the same plane as line AC, it either touches AC, which is an intersecting line, or it's parallel to AC. Those are my only two choices. Okay, it either touches it or it intersects. Did not say what I meant there. It either touches it or it doesn't. So it either touches it or it's parallel. This is what happens when we have two lines that are in the same plane. Okay, in the same plane has a name just like on the same line. In the same plane is coplanar. So if you have two lines that are in the same plane, on the same plane, they could either be parallel or they could intersect. Now there's also a thing, which is a line that's not in the same plane with another line, and it has a special name. So I'm going to pretend I have a line that goes through this plane vertically, kind of punches through it right there at point B. These two lines are not parallel. They also don't touch each other. Okay, so those are non-coplanar lines. And the name for that is skew lines. So skew lines are lines, they're the third option. If you have two lines, either they're parallel, or they intersect, or they could be skew, which means they're not in the same plane at all. One good example of skew lines is when you're driving down the road. If you come to an intersection, well, that's intersecting lines. Okay, and if you think about it, I wouldn't do it, but you could stand out in the middle of an intersection, maybe a cop directing traffic. If he's standing out in the middle of the intersection, then he is on both lines at once. He's on both roads at the same time. All right, but think about an overpass. Think about when you have a road that goes underneath an overpass, and I know I'm not going to draw this as well. And then it comes out over here. Like maybe right beside Taco Bell on Five Forks. That's an overpass where Ronald Reagan goes over Five Forks Trickham Road. Or where else do we have overpasses? There are a lot of places, but that's the one that comes to my mind immediately. And this road down here, there's no way for me to stand on this road and also stand on this road. That means there are no points in common. That means those roads don't intersect. They are skew. So that's a sort of a real life example of skew lines, is like a road and then another road that passes over it on a bridge but never actually touches it. They're not parallel. They're not equidistant apart, equal distances apart the whole time. We haven't used the term yet, but the geometry term for that is equidistant. I was kind of avoiding using it. But like on this one, the closest these two lines ever get is right here in the plane. But they're not touching. Okay, and they don't stay that distance apart forever, because parallel lines do. Parallel lines are always the same spacing apart that they were to begin with. I can't find my parallel lines. Here they are. They're always going to stay the same distance apart, but they have to be in the same plane to do that. Okay, and that is it. Oh man, I didn't make it. I thought I was going to make it to the end of this video without my cat running across underneath the camera, and I did not make it. That was a cat, ladies and gentlemen. A very quick cat, but a cat nonetheless. We have one more video to talk about some basics, and it's just a few more things. It's about angles. So stop here. Go ahead and review what you need to review about lines and segments and points. And then you need to watch the last little bit about angles, and you will be golden and ready to talk about all things geometric. Thank you for joining me. See you later.